Hello everyone. Thank you very much for joining. Actually, let's keep it informal. Hoi, everyone. And also, I would like to make a special thank to my friend Samer, who came all the way from Paris. He is also known as Sam. Actually, he's not my friend. I should tell the truth. He's like a brother, but from different parents. Welcome. So, welcome to the presentation of my defense. Ultra-narrowband communications, a feasibility study for the 2.4 GHz band. By ChatGPT, sorry, by me. Awkward. So what's ultra-narrowband? Well, ultra-narrowband is simply a signaling scheme with a very low instantaneous bit rate. It's the opposite exactly of ultra-wideband. Well, you would think, why would you need ultra-narrowband? Why would you go for ultra-narrowband? Because everybody wants higher data rate, higher bit rate, right? Well, if you do so, that will allow you to shift the burden in terms of processing load and also in terms of power consumption, shift that burden from the nodes, the wireless sensor nodes, to the base station. And this is already actually deployed commercially in the 868 MHz ISM band to provide radio access coverage. So you can tell by now it's not for the average Joe to provide internet access. Imagine you have internet access of 100 bits per second. It will be taking forever to download a game or a video. So it is only for latency tolerant and low throughput wireless sensor networks. So if it has already been deployed in 868 MHz band, what's the issue? Well, we researchers would like to make some problems and then propose solutions to those problems. So there are actually two issues. The first one is that there's a rapid growth in the number of wireless sensor network devices and Internet of Things nodes. As you can see from the figure, currently there are more than 10 billion, yes, billion Internet of Things devices that are already deployed worldwide. And that's excluding smartphones, tablets, and laptops. So that was the first issue. You need to accommodate that, especially for the future. As you can see, the curve is exponential in growth. The other issue about the 868 MHz band is that there are two sub-issues, actually. The first one is that there's a limit on the bandwidth of roughly 8 MHz. That bandwidth is, of course, imposed by emission regulation. But also, more importantly, there's another limit, which is a very harsh limit on the duty cycle. And that actually translates itself to roughly 140 packets per node per day. Yes, only 140 packets per node per day. And each packet is roughly like 12 bytes or something. So because of those two issues, we think of some alternative. Why would not we go to a different frequency band, to the 2.4 GHz band, also known as the Wi-Fi band? Okay? Because in that band, the available bandwidth is much larger, which is roughly 80 MHz, and also there's no harsh or not even duty cycle limitation. And that's what my project was about, to investigate the feasibility and also to accomplish an ultra-narrowband deployment in the 2.4 GHz band. So we need to investigate that feasibility in terms of energy efficiency and wireless coexistence. Not only that, but also in order to accomplish a deployment in the 2.4 GHz band, you need first to develop some kind of experimental environment, specifically a cost-effective experimental environment. So that was my research project. And you can see, you can easily extract the first research goal. The question was, when it comes to feasibility in terms of energy efficiency, what are the suitable deployment scenarios for the ultra-narrowband signaling scheme in the 2.4 GHz band? I will save you from the details of what I did over the years. I will skip immediately to the conclusion. And I will give a quick conclusion. Well, ultranarrowbands, it turns out it is an energy-efficient RF solution when a very large link budget is needed, either to cover a very large distance or to combat frequent fading dips. The other identified deployment scenario is that ultranarrowband, UNB in short, represents a convenient ultra-low power RF solution for wireless sensor network nodes which are tiny with very harsh peak power consumption limitation, as in energy scavenging power sensor nodes, green sensors project. I would recommend it for you. So that was the conclusion of the first research goal. However, I would like to convey a message here, and I'm switching to my lecture mode because I'm used to giving lectures. Well, in real life or even in research, you are faced with multi-element problem. If you have a multi-element problem, I would recommend not to consider all the elements at once because most likely you will reach a dead end. So for example, if you have the 3 elements in the problem, I would recommend you to consider only one of them at once, assuming all the others do not exist. And you would find that the solution is easy. And you move on to the next problem, again at once, assuming all the others do not exist. And you solve it. After that, you combine 2 elements at a time, again assuming the 3rd element doesn't exist or already solved. Wish me luck. Okay. After that, and only after that, you consider all the elements in the problem. And that's what actually I teach in Module 8. Where's my student? Cheers. Okay, again, wish me luck. Oh, okay, almost. That would be enough, I guess. Back to the presentation mode. So that was the key message I wanted to convey for the first research goal that I learned actually myself when I was doing the research in that and working with that chapter. The second research goal, the question was, in case of a future deployment in the 2.4 GHz band, how friendly is ultra-narrowband signaling scheme to Wi-Fi? Because Wi-Fi is almost everywhere, even in you have free city Wi-Fi. Again, I will skip immediately to the conclusion, is that on-off keying baseband ultra-narrowband signals are the least interfering impact, have the least interfering impact on Wi-Fi. And also, the Wi-Fi pilot subcarriers are the most vulnerable to the ultra-narrowband interference. And from this insight, from the empirical investigation I did and the methodology I developed, I figured out that I can recommend 17 subbands for ultra-narrowband in order to promote friendly coexistence with Wi-Fi, as you can see in the figure. Again, I would like to convey a different message here that I learned during my work on my PhD. And also especially working on a conference paper that relates to that topic. I noticed that most people follow one of those 2 approaches, either the zero risk approach, obviously you can read it, or the maximum risk approach. Well, why not follow something in between instead? Why not every now and then take a little bit of risk? Because I read somewhere, actually, I don't remember who said so, and I read somewhere that the biggest risk is actually not taking any risk. It says gratis. That means I won another scratch card. It's an endless loop now. Back to the presentation mode. The third research question was, considering the potential deployment scenarios from the first research question, to what extent can the vibrating intrinsic reverb chamber be used as a channel emulator for ultra-narrowband? Again, very quickly, skipping to this conclusion is that the work can roughly be used as an ultra-narrowband channel emulator with ascribed first and second order temporal and spectral characteristics in general, but with limited emulation capability on how slow the fading can be in particular. Again, another key message that I would like to convey here, that also I learned while I'm working on this specific research question, is that when you build your measurement setup in order to measure some phenomena or measure the performance of some device, the worst thing anyone can do is this. The worst thing anyone can do is to choose the default values in the settings of the instruments, especially in the vector network analyzer, the VNA. And I learned that the hard way myself. And with this, I would like to conclude with my presentation. And thank you again for joining and laughing at my awkward jokes. Thank you very much. So, did you like it? I was sweating. You can imagine how much I was sweating inside.
The worst part is over now, so okay.
Yes. Actually, I prefer standing. That's okay. Good luck for you guys. It's very easy. Trust me, it's very easy. How much work? So in the end, I want another scratch card. Who would like to take it? And start a chain reaction. Okay, let me do it. Okay, I will close my. Who took it? No one? Oh, no. No.
You have some. Which microphone do you prefer? This one or that one? Take this one off. And like I said, just pull it towards you. You should stay here.
Anyone has a story?
Please be seated. I open this public meeting of the Doctorate Board of the University of Twente. I would like to express my welcome to all of you, in particular to the family and the friends of the candidate. A special welcome is extended to the members of the committee. We have online Professor Mariani Primiani from the Università Politecnica della Marche in Ancona, Italy. Welcome to Twente. We also have Professor Smolders of Eindhoven University of Technology. Also welcome to Twente. And from the University of Twente itself, we have two members in the committee, Professor Heijenk and Professor Slump. Also present are the promoter and the co-promoter. The promoter, Professor Kokkeler of the University of Twente, and the co-promoter, Dr. Glasunov of Linköping University in Sweden. Could the candidate and without his paronyms come forward, please? Dear candidate, are you ready for your defense?
Highly esteemed rector, yes, I am ready.
Very good. May I ask Professor Mariani Primiani to start the opposition?
Good afternoon.
Good afternoon.
Please start the opposition.
I wish to ask you some questions about your work. First of all, I wish to ask you if you have noticed some dependence of the parameters of the beard on the position of the absorber inside it. You have chosen a particular position, but you experience about what happens in case of change in position. Second aspect is related to the using of the metallic corner wide the probe inside the anechoic chamber. Why don't use an absorber corners, which is the reason for a reflecting corner and not an absorber corner? And the last question from my side is, what do you expect for extending this procedure to broadband systems? What kind of problems do you expect that can arise?
Highly learned opponent, thank you very much for the intriguing questions. I hope I remember all of them. I may ask for your help and repeat one of them or two of them. So let's start with the first question. So if I still remember correctly, your first question was, what was the impact of the locations of the observers inside the Verk reverb chamber on the parameters that or the characteristics that I measured or estimated? Well, my answer to that, of course, they have some impact on the constants of the models that I proposed to characterize the channel first and second order temporal and spectral characteristics. So as I showed later in the chapter 5, when I investigated a different framework setup, different work setup and different channel setup by placing different absorber and in different location and also using different antenna orientation and location, etc. I was able to show that all the models indeed can be generalized regardless of the location of the, for example, in this specific case, the observers. However, of course, the constants of those models will change accordingly. And that will, of course, also affect some of the end characteristics that I focused on, like the coherence time and the coherence bandwidth. Nevertheless, the methodology I developed was universal in the sense, as long as you follow the steps, step 1, step 2, step 3. In the first step, you measure and estimate the second order temporal characteristics first, and some of those parameters that you estimate, you move on and use them in order to set the settings correctly for the measurement setup for the second step, which was concerned with the second order spectral characteristics, and the same thing again for the third step. If you do that, you are guaranteed, at least that's what I claim in the thesis, that indeed all the models that you will try to fit the characteristics that you measure will indeed fit, with, of course, with different constants that you can measure and according to the fitting algorithms it use. So that was the first question.
Okay.
The second
Thank you for the
question,
answer.
sorry?
Thank you for the answer.
Thank you very much.
Very good.
For the second question, would you repeat, please, the second question, my highly learned opponent?
In the anechoic chamber setup, you used a reflecting corner to hide the probe. I remember a reflector corner that you have inserted in the chamber. So since you are inside an anechoic environment, why don't use an absorbing corner? So, or did you try to do that and there are no many differences? No.
My highly learned opponent, again, thank you for the intriguing question. So your question was about the wireless coexistence, the measurements of the wireless coexistence between ultra-narrowband and Wi-Fi inside the anechoic chamber, and why I used an absorber in front of the probe.
Yes.
And the probe
instead of a reflecting.
Yes. When I was building the measurement setup, I was first concerned about how much interference that I will get from ultra-narrowband signal on the probe that I use to probe the spectrum and also collect the Wi-Fi packets to monitor the channel and at the level of the physical layer to collect the Wi-Fi packets to see what kind of modulation coding scheme and bitrate that are being transferred. So I use a corner reflector because the corner reflector has a specific feature that any signal will be reflected completely back in the same direction that it came from. At the time, I was concerned about this, but I would actually agree an absorber would actually also work as long as the absorber is placed in such a way that the orientation is directly to the signal that's coming from both the Wi-Fi signals, both of them, at the access point and the station, and also ultra-narrowband signal, interference signal. Because if I know, and please correct me if I'm wrong, the absorption, the equivalent absorption that you get actually also depends on the angle of arrival of the signal to the absorber.
You are right. Yes.
Yes. So I would agree, indeed, an absorber could be used instead of a reflector. And for the third question, again, would you please repeat it?
Which is your opinion about the extension of this procedure to broadband systems? What kind of problems do we expect in doing this extension for the future, of course?
My highly learned opponent, thank you again for this intriguing question. For the broadband, or also you can call it wideband measurements for wideband channels and wideband systems.
Yes.
I would argue that the methodology that I developed is also fully applicable to wideband. The only thing that needs to be tweaking, or not exactly tweaking, to be added, is a little bit more focus on modeling of the frequency autocorrelation function. Because from the frequency autocorrelation function, which I also in my measurement setup and in my methodology, I estimated in order to extract the coherence bandwidth from. If you add extra sub-step in the investigation step 2, you can also investigate the frequency autocorrelation function and convert it using inverse Fourier transform to power delay profile, and then you can know what kind of channel you have for in case of wideband measurement, in case of measurement for that considers wideband channel. I hope I answered the question correctly.
Yes. Yeah. I think that this is the key point, the autocorrelation function, the frequency domain.
Yes.
Thank you, and
thank you.
You also for excellent work.
Thank you very much.
Yeah, thank you very much, Professor Mariani Primiani. May I now invite Professor Smolders to ask his questions?
Thank you, meneer de rector. So, dear candidate, let me first say that congratulations with your thesis. It was really a pleasure to read and also to see that you covered quite a broad range of topics. That's appreciated, especially also the experimental work. And most of my questions are about the reverberation chamber, but I would like to kick off with a more general question. In your introduction, you motivate a little bit why you use 2.4 gigahertz, but I had the impression that you used 2.4 gigahertz because your supervisors told you so in the beginning. And that the project proposal was written around 2.4 gigahertz, which is good, you know. You have to limit, you have to have some focus in your work. So it's not that I want to be critical about that. But now, after 4 years, you've done a lot of work and you build up a lot of insights. Do you still agree, you know, with your supervisors who made a proposal that 2.4 gigahertz is a good choice for this?
My highly learned opponent, thank you very much for your kind words, and also thank you very much for the intriguing question. If I want to come clean, there's part of truth, there's a little bit of truth in that, in what you have stated. Indeed, the project proposal was written, and then I was accepted as a PhD candidate for that project proposal. However, I would like to mention that in the project proposal, there was no specific mention for the 2.4 gigahertz specifically. So the ultra-narrowband signaling scheme in the project proposal, there was an open question about which frequency band we should consider. And only later, at a later stage, I decided, based on the work I focused on, especially the wireless coexistence, it would make more sense for a coherent story of the thesis is to consider only 2.4 gigahertz band. And regarding the second part of your question, if I would agree that the 2.4 gigahertz is a good candidate, band for the ultra-narrowband, I would argue the answer is neither yes or no. It's not a straightforward answer. The issue is that in the 868 megahertz band, in which the ultra-narrowband signaling scheme was already deployed and commercially implemented, is that there's two limitations in that band, according to emission regulation. The first one is the limited bandwidth of roughly 8 megahertz, and the other one, which is very harsh limit, which it was imposed on the duty cycle, which means there's only, according to my calculations and also in the literature, there will be roughly around 140 packets per node per day that the node can transmit. And given that there's an explosion in the number of wireless sensor networks all over the world, and currently, according to some of the estimations, there are billions and tens of billions of them. So we need to find a solution for that. We cannot just say 2.4 gigahertz is not suitable. We need to investigate it, and that's what we did. There's caveat here, so the 2.4 gigahertz is also filled with ultra-narrowband interference, with a lot of interference from Wi-Fi networks, Bluetooth, Zigbee, etc. Nevertheless, as I figured out, there are actually two good candidates for the 2.4 gigahertz band for the deployment. The first one is that if you need to cover a large distance, like an indoor campus environment, and you want to use only a single base station to cover the whole area to provide radio coverage for the sensor nodes in that building, then ultra-narrowband is a good candidate, and it can indeed be friendly to other Wi-Fi, to other networks that are already deployed in the 2.4 gigahertz band, especially for the Wi-Fi, as I showed in chapter 2. Regarding the second deployment scenario that I also identified, that it was, you can use ultra-narrowband for wireless body area network in which there's a communication link between a base station, off-body base station, to an on-body sensor node. That sensor node, according to the identified, again, deployment scenario that I investigated, is that if that node has a very harsh peak power consumption limitation, like in energy scavenging power sensor nodes, and the node is very tiny with the crystalless design, that indeed ultra-narrowband is a good candidate. And I would also recommend it, as I mentioned in my layman talk, that it is a good candidate for the green sensor project, which as far as I know, it's a collaboration between many institutes, including Twente University and TU Eindhoven.
Yeah. Okay, but you're still enthusiastic about 2.4, so that's good. I want to move on to my next questions, else we run out of time. So I would like to start with figure 4.1. I don't know if you can put it on the screen or something, or doesn't matter too much, but it's the setup that you use, and maybe it's a trivial question, but I still want to ask it. You use a vector network analyzer in your setup, eh? Now that's a relative expensive machine, eh? And so I wondered, could you have also used a more simple setup, and what would be the limitation? For example, a setup where you have a signal generator and a power meter.
My highly learned opponent, thank you very much for the intriguing question. So when I built the measurement setup, I used indeed an expensive tool, the VNA from Agilent Technologies. Regarding your part of the question, would it be advisable or would it be wise to use a signal generator and a power meter? The answer, I wouldn't recommend it for my methodology because some of the parameters that you need to estimate requires the complex baseband. So the signal will be converted from RF to baseband in complex, and will be represented as complex numbers. So you need the amplitude and phase. If you want to use a power meter, there will be a limitation because you will be losing the phase information, which is crucial to estimate most of the parameters I needed for that channel in order to investigate the channel.
Yeah. Yeah. Okay. Thanks. Another question is about figure 4.10. And you know, I'm into antennas and stuff like that, huh? So you present the efficiency of the antenna that you use, or the antennas, and then I was a little bit disappointed because I think the reverberation chamber is the ideal instrument to measure the efficiency of antennas, much better than in an anechoic facility. And then you measured in an anechoic facility. So can you explain why you didn't use the reverberation chamber?
My highly learned opponent, again, thank you very much for the intriguing question. So this matching efficiency that I reported in figure 4.10 is for the matching efficiency, which means you don't need a specific setup to measure it. It's the only thing you need to measure is the S11 parameter. Of course, as long as you put some absorbers in front of the antenna so that there's no reflection from the environment, so that the reflection from the environment wouldn't affect the S11 parameter.
Yeah, but I guess that you also would be interested in the other loss mechanisms of the antennas, or were they so low that you could simply neglect them?
So regarding this measurement, I needed this one as a guideline, the matching efficiency as a guideline to explain what happened later, to reason out some of the results that I got.
Yeah,
however,
yeah.
I believe that the efficiency that you are mentioning is the radiation efficiency, which indeed can be measured in the either the anechoic chamber, which is very cumbersome process, or in the work chamber, which is...
Yeah, you mentioned that later in
indeed.
your thesis as well.
Yeah.
But maybe to continue a little bit with this antenna, so these antennas you used in the setup, so two of them, as I understand. Now you state somewhere that they are kind of omnidirectional antennas, but then I wonder, is it possible to make an omnidirectional antenna which is so broadband? Do you not expect that they will be very directive at the higher frequencies? And would that change your measurement outcome or the conclusions that you draw?
My highly learned opponent, again, thank you very much for the intriguing question. So regarding the omnidirectional antenna, The one I used is from, if I still remember correctly, from Cisco vendor, that is usually provided for its Wi-Fi and multi-band devices to cover different multi-bands, LTE band, Wi-Fi bands, etc. And that omnidirectional antenna is specifically mentioned in the datasheet. It's broadband antenna. It's not wideband antenna, which means it has very good performance in some of those bands, while it has poor performance in others, like figure 4.10 indeed shows regarding the frequency range from 1 gigahertz to 1.2 gigahertz when I measured the matching efficiency.
Okay. Another question I have is also related to these antennas, but then more to the setup. Let's say figure 5.2, for example. 5.2, yeah. So where you have this configuration with two antennas and these absorbers and stuff like that. So I wonder, is the location and the orientation of both antennas, is that an important factor in your measurement, and what's the effect of it? Did you investigate that as well? Or?
I highly learned opponent. Again, thank you very much for the intriguing question. Regarding this specific location of the antennas, I did not investigate different location of the antennas and different orientation other than for the last part of the chapter itself, where I investigated the generality of the models by placing the antennas in different location and orientation. However, I would like to mention here that I have followed the recommendations and guidelines from electromagnetic compatibility community and the standards that you need to place your antennas within the working volume of the chamber. That's one. Number two, there's also a guideline in order to minimize the K factor. If I would like to emulate a near Rayleigh channel, you need to minimize the K factor of the channel, and that means you need to put the antennas cross-polarized. However, the location of the antennas doesn't matter. The only thing that matters, according to the formula of the K factor, the theoretical K factor of the chamber, is that you need to put the antennas as far away from each other as long as they are in the working volume, number one. Number two, the orientation should be also minimum towards each other, because in the formula there's the directivities of each of both antennas in direction of each others. And that would actually also sacrifice your K factor if you put them orienting to each other. So that's the guideline mainly, if I still remember correctly, those are the guidelines mainly I used regarding the location.
Is there any time left? No?
I'm afraid not.
Okay.
We have to continue.
Okay, thank you for your answers.
Thank you.
Thank you very much, Professor Smolders. May I now invite Professor Heijenk to continue the opposition.
Thank you, Mr. Rector. Dear candidate, congratulations from my side for this very interesting thesis, where you cover really a wide range of topics revolving around ultra-narrowband communications. Sorry for that. I especially enjoyed reading the parts about energy efficiency and wireless coexistence, as you may understand. I have a few questions about both topics. To start, on page 25, you introduce an optimization process for energy-efficient ultra-narrowband communications. And there, basically, as input, you take some design constants and deployment parameters. And then later on, you're going to optimize certain design parameters. The assumption there is that you kind of have at design time exact knowledge about the deployment. And for instance, you fixed the link budget before doing the design. And I could imagine that you would like your system to operate under a wide range, quite a wide range of possible link budgets. Could you think of how to optimize your system under such circumstances, so that you optimize before actually fixing the link budget?
Okay, my highly learned opponent, thank you very much for the kind words regarding the thesis, and also thank you for the question. Unfortunately, I would like to disagree with your highly learned opponent. I did not fix the link budget. In fact, it was actually a range I investigated the optimal solution of the bitrate for a wide range of of link budgets, and also a wide range of limitation on the peak power consumption. So I did not actually start with the link budget. It was part of the investigation, like what happens if your distance becomes larger, or if you experience frequent fading dips, which means you need to accommodate that in the link budget as a fading margin. So in fact, I did not fix the link budget in the optimization process.
You did consider for, a wide range of link budgets, but the assumption is that you are going to fix at some point in time, at design time, the bitrate that you're going to use in the uplink and downlink.
Okay, thank you very much, my highly learned opponent. Now I fully get what you mean by fixing the link budget. Indeed, in study case 3, I considered, after study case 1 and 2, where I considered what happens to the optimal bitrate for different range of link budget and peak power consumption, I considered in study case 3, what happens if you fix the bitrate to 2500, assuming it's the maximum ultra-narrowband bitrate that you can use, and claim that this is ultra-narrowband. And I showed indeed, if you don't follow the optimal solution of the bitrate, but you still follow the optimal solution, or at least the minimum radiated power, given that you know somehow the link budget in practice, that indeed you would get energy deficiency in the solution that you get. So regarding the link budget, I assumed in study case 3 somehow the node knows the distance. I didn't investigate, or I didn't mention how the node can know the actual distance and actual fading margin. I just assumed that it knows, and then I assumed that there's a transmit power control mechanism that it tracks the optimal solution in this specific case for the radiated power.
So you would be close to optimal for a wide range of link budgets?
Trying to be close to optimal, but fixing the bitrate actually causes an energy deficiency in the solution. And that energy inefficiency, according to the numerical example I considered, accounts for up to 13 dB, if I still remember correctly, for very low link budgets, while it becomes very small for higher link budgets.
Yeah. Thank you for this answer.
Yes.
And maybe along the same lines, and I know this is done often in other work as well. You also fix the desired bit error ratio or packet error ratio. You could use it as a degree of freedom. I mean, in the end, of course, the desired one would be 0, which is not achievable. So you do retransmissions, most likely. At least I see an acknowledgement scheme, so you do retransmissions. You could use that also as an optimization parameter. Have you considered that, and what would be the influence of that?
Thank you again for the intriguing question. It's very intriguing and difficult question. Highly learned opponent. I wouldn't actually optimize the bitrate, because the bitrate or packet error rate is specified according to the application and the quality of service of that application. Usually there's an upper limit or lower limit on the performance of the quality of service of the application. So optimizing the bitrate wouldn't be the approach I would follow, actually. Because again, for the application, it's usually the quality of service is defined, and then from it you extract the packet error rate or bit error rate given a specific modulation or coding scheme that you use.
But typically the desired or the requested error ratio is kind of 0, which you basically achieve with a retransmission scheme.
Yes, indeed. Indeed, that can be also a choice, is to retransmit the packet in case if it is corrupted by interference or by fading dips. Indeed, that would be also a choice.
Okay, let's move on to chapter 3 about wireless coexistence. You start with a statement on page 43 that IEEE 802.11n is the latest widespread Wi-Fi version in the 2.4 gigahertz band, which I think at some point in time it was true, probably at the time you have done the work. At the current point in time, that's, I think, not true anymore. I think currently the 802.11ax standard is the probably most widely deployed. And it provides considerably higher data rates. And I understand that you haven't done this work, but can you hypothesize on how the impact of ultra-narrowband communications on Wi-Fi is affected by these new standards? And maybe to help you a bit, I mean, one of the features there is higher modulation, so 1024 QAM. Another one is OFDMA rather than OFDM.
I highly lean upon it. Thank you again for the intriguing question. So regarding more advanced versions or latest versions of the Wi-Fi, indeed there are different actually mechanisms that are added to the standard. One of them is indeed higher modulation coding schemes. And I would argue that the higher the modulation coding scheme becomes, is actually more vulnerable to interference. That's what the investigation also showed, and it was also confirmed in the literature. However, that was not the only thing that the new standards added to the previous standards. There are actually different MIMO techniques, like beamforming, spatial diversity, and spatial multiplexing. And in case of beamforming, there are actually two schemes usually, like the interference nulling in case of receiving beamforming, or transmit beamforming in case of transmitting beamforming. And in that case, in case of that technique is used in the new version of Wi-Fi, that indeed it will be now less vulnerable to interference. Putting the beamforming technique aside, there are the other two techniques in MIMO that are actually added by the new version of Wi-Fi. There are the spatial diversity was actually already in version, and the spatial multiplexing. So spatial diversity is usually used to combat multipath propagation in order to improve the overall packet error rate, while the spatial multiplexing actually is used to exploit the multipath propagation in order to improve or increase the throughput, the total throughput, by increasing the channel capacity. I would argue that in higher versions, because they define higher order modulation schemes, that means there are plenty of antennas that are available, multi-element antenna, that are available in the Wi-Fi access point. And in that case, as I said, beamforming can be used, and it would be very efficient in combating the interference. But also, I would argue that if in case that the beamforming was not used, that depends, of course, on the setup between the access point and the station, that the ultra-narrowband interference may have also an impact, a significant impact on the spatial diversity or the spatial multiplexing scheme that's proposed in the new version.
Yeah, thank you.
So it is an open question.
I see some signs from Mr. Rector, which I interpret as there's no time for an additional short question, right?
Very good interpretation.
Thank you.
Thank you very much, Professor Heijink. May I now invite Professor Slump to ask his questions.
Dank u wel, meneer de rector. Dear candidates, you have written a very interesting thesis. The topic is very interesting. At some pages I had difficulty reading it because you use a lot of acronyms, and so that makes the reading somewhat difficult for me, because I have problems remembering all those acronyms. You also say that ultra narrow band is also an acronym. You do so on page 9, right?
Yes.
Would you comment on if that's UNB is the most often used acronym in the thesis?
My highly important, thank you very much for the kind words and also for the interesting question. Most likely it is actually. I didn't check, but I believe it is true.
Okay, but it's not in your acronym list.
That's partially true. So that's true actually. However, in chapter 1, I mentioned in the footnote, so it would be very tricky to find it, but I mentioned in the footnote that ultra-narrowband UNB from now on will be used as an acronym.
Yes, it's on page 9, in the footnote on page 9.
Yes, that's true indeed.
Okay, it's clear.
Okay.
Also on the page 9, you make a statement that a certain view is logically false. Now, what do you mean by it can be factual false or just false, but logically?
Highly not important. What I meant at the time when I wrote that statement, logically false, I wanted to emphasize that it is widespread. So logically can indeed be dropped here, since that statement is false. That I would like to spread the awareness about.
Well, I wasn't quite convinced. I was probably fooled by the statement then. I have another question. That's slow wireless project. Is that a misnomer? Is the project slow, or because the transportation speed of the electromagnetic waves is close to the light speed, isn't it?
Highly important. Thank you for the interesting question. It was actually the title of the proposal that was submitted and was accepted. It was slow wireless, and it meant that the communication link in terms of data rate is very slow.
Okay, so it's not that you had to work slowly. Okay. Well, makes it clear. There are several ways I can now proceed. I like to go to page 75. Because there, and on page 75 and page 79, you talk about a chicken-egg problem.
Sorry, again? What?
Chicken-egg problem, page
Yes.
75.
Yes.
And, well, I have some experience in biomedical research, so I was interested here. So you say, okay, this creates a situation similar to the chicken-egg problem. To break the latter, so you break the egg, a heuristic approach is followed. Okay, so you break the egg, but then you won't have a chicken, right? And then you won't have a new egg. So how does this help you to solve the problem? Okay, and then you make a statement you make 3 statements, and you have 8 rough estimates, and then you do a nonlinear regression. And are you sure that you get a unique answer there? That's my question.
My highly learned opponent, thank you again for the intriguing question. Regarding the egg-hen problem, it's a common phrase to show the dilemma that one part depends on the other. So it's an endless loop, and that's what I actually was facing when I wanted to measure, for example, to estimate the coherence time. I figured out that some of the parameters, the settings in the VNA and the measurement setup actually needs beforehand to know what the coherence time you want to measure, which, as I said, creates like an egg-hen problem. So what I did is that I followed a heuristic approach. So I made some assumptions and I used them as guideline. One of those assumptions is that I measured the peak configurations, the extreme configurations, and from them I used an initial estimate for the coherence time, and I used that also to do some nonlinear regression, as I mentioned in the thesis. assuming that this is a plausible assumption that the coherence time is inversely proportional to the rotational speed and also to the carrier frequency, as been also reported many times in literature. However, I didn't use those preliminary estimations in the final reporting because I used them only as a guideline to set the parameters in the VNA. So they helped me just to find a scope, to specify my scope to where actually look at.
Okay, and that's then your, say, optimal solution or the solution you want to have. Just on the same page 75, you make a statement, and it says, finally, it can be easily proved that the relative width of the expected confidence interval of the estimated coherence time is approximately equal to that of the estimated normalized time autocovariance function, as long as the latter is less than 35%. You easily proved. Well, this took me quite a while, few headache pills, and I'm still struggling with this statement. But you say it's easily proved. Can you give us a hint how this is done?
My highly named opponent, thank you for the intriguing question. So in this statement, what I meant by the word easily is that it can be derived with the given that the basic knowledge of mathematics is there. However, I missed something very crucial, and I agree with you that this statement is lacking very crucial information that I mentioned only at the beginning of the methodology on page 73. Sorry, not 73. On page 74, actually, the previous page, when I mentioned that I assumed by starting when I started my methodology, building the methodology, I assumed that the channel, in this specific case, the autocorrelation function or the autocoherence function, is upper bounded by an exponentially decaying function. So you need that information, and I fully agree with you in that case. You need that crucial information in order to figure out how easily it becomes actually when you try to figure out the variation horizontally in the estimated coherence time, given the variation vertically in the autocorrelation function.
Okay, yeah, I understand. You have made a design and also realization of a channel emulator or channel simulator. If you now look back at page 19, then you make a whole list of assumptions, and then you say, okay, for the sake of simplicity of the analysis, we make the following assumptions. Nevertheless, they will not significantly impact our outcome of the optimization process. How can you be sure about that? Yeah, because you make AWGN channels, which are, I don't know if they exist physically. You do a lot of assumptions about power, etc.
My highly learned opponent, thank you again for the intriguing question. So what I meant by this statement, which actually I agree it could be misleading in statement, is that they will not significantly impact the outcome of the optimization process, is that the methodology itself will not significantly change that I used in order for the optimization framework itself will not significantly change. However, the numerical example or the numerical values that you will obtain from the optimization given application, indeed, it will significantly change. If you change, for example, one of the assumptions regarding the AWGN channel into...
Okay, yeah, I understand. I had difficulty understanding your design because you don't make a clear statement about your design goals. It's a bit vague, I would say. So I think you started implementing it and using the best Twents knowledge, kicking what. And I think that's what you have.
Geachte rector, de tijd is verstreken.
Thank you, Mr. Bido. Can I ask the candidate to take his seat? I adjourn this public meeting of the Doctorate Board of the University of Twente. Please be seated. Ladies and gentlemen, I reopen this public meeting of the Doctorate Board of the University of Twente. Can I ask the candidate to stand before this table? The Doctorate Board of the University of Twente, represented by us, has examined your dissertation and heard your defense. The Committee of Deans has decided, in accordance with Article 7.18 on the Law on Higher Education and Scientific Research, to admit you to the degree of doctor. I request the promoter to carry out the appointed task.
Under the authority assigned to us by law, and on behalf of the Doctorate Board, I grant you, MHD Zaher Mahfouz, the degree of doctor and all the rights that are attached to this degree. As evidence of this, we present to you this diploma. Signed by the Rector Magnificus, the Secretary of the Graduation Committee, and your promoters. Validated with the seal of the University of Twente. Yeah. Zaher. Congratulations, Zaher. To the audience as well, I think. Shall I put it? Okay. Shall we just leave it over here? Okay. Don't forget it, eh?
Dear learned doctor, let me congratulate you also on behalf of the university on your acquired dignity. From now on, you have the right to use the title of doctor. This title implies that society can rely on the quality of your judgment, that you will act with integrity and transparency, and that you will communicate independently about the results and the social relevance of your work. Voted doctoraal is an honorable distinction and well-deserved prerogative, but always remember the obligations imposed by it towards the scientific community and society. Next is your co-promoter, Dr. Klaasjonov.
Thank you, Mr. Chairman. Am I allowed to take a picture with the candidate?
Nou, voor mijn eerste laudatio.
Okay. Dear Zaher, today we gather to celebrate the culmination of your intellectual journey, which has led you to a well-deserved achievement of a PhD here at the University of Twente in Enschede in the Netherlands. Your academic odyssey began in the ancient city of Damascus, Syria, your place of birth. Is it ancient? But it's not because it's not your. I mean, you're not that old. But anyway, and driven by insatiable thirst for knowledge and relentless pursuit of freedom, you ventured to Malaysia, where you attained your Master of Science degree. Your exceptional performance as a top electrical, electronics, and communication student, together with your innate curiosity, laid the foundation for your eventual pursuit of doctoral research here. Well done. Our path crossed in Twente, where you were already deeply immersed in the slow wireless project within the communications engineering group. Soon after, you kindly accepted the secondment to Gap Waves in Gothenburg under the European Commission-funded ISTRI-DIMAIMO RISE project grant, a decision that I suspect was motivated by more than just the appeal of beauty. Your time at Gap Waves and Chalmers not only allow you to solidify your expertise in MIMO antenna measurements, but also breathe new life into your research pursuits. This is invaluable because in the latter part of your doctoral thesis, you embarked on a comprehensive exploration of the Virtual Intrinsic Reverberation Chamber, the VIRC, a creation of Professor Frank Lefferink here at the University of Twente. It is fair to say that you, Zaher, were perhaps the first to conduct an extensive
experimental investigation into the fundamental characteristics of the work, but was initially conceived as a short letter evolved into the foundation of 3 full-length journal papers comprising half of your doctoral thesis. Your work explored the work's ability to emulate the ultra-narrowband propagation channel. As a result, you introduced a systematic measurement and estimation methodology for empirically characterizing the channel. This methodology possesses universal applicability to reverberation chambers operating under the Mohs theorem regime, promising significant utility in the testing of ultra-narrowband devices and algorithms, and in general as well. Your persistent pursuit of excellence has, figuratively speaking, turned the fantastical goal of not-chemist into reality. Well done. You have consistently demonstrated the spirit of a true scholar, a relentless pursuit of knowledge to uncover this profound meaning. Advancing knowledge for the greater good requires not only the quest for understanding, but also the duty to communicate one's finding to have a meaningful impact. And you have done that. Time is a peculiar concept, often perceived as fleeting due to our limited ability to observe the physical world. Yet, time sets the boundaries for many endeavors, including the demanding task of writing, a challenge faced by most doctoral students. It takes considerable energy to transform chaos into order, and it requires substantial amount of negentropy to conquer the common affliction that plagues writers. As Douglas Adams famously remarked, I love deadlines, I like the whooshing sound they make as they fly by. But now you, Zaher, have an important deadline that you have achieved that marks the start of a new chapter in your journey. Congratulations. Dear Zaher, over the past years you have transitioned, damn ChatGPT, transitioned from being my student and colleague to becoming a cherished friend. I treasure our diverse conversations, ranging from Knafe, which also we tested, to enigmatic mysteries of existence and science. I have learned a great deal from you, and for that I am immensely grateful. May your future endeavors be met with success and fulfillment that you so rightly deserve. And best of luck with your Icelandic explorations.
Again, congratulations also from my side. I still have a small present for you, your own thesis, but now with all the signatures of the committee.
Thank you.
In a moment we're going to leave the room. First the beadle, then the young doctor, then the committee, and then the rest of the audience. And also will be occasion to interact with Professor Mariani Priami at some point in time. Can I ask the young doctor to take his seat? I close this public meeting of the Doctorate Board of the University of Twente.
My dear Professor Mariani Priami, thank you very much for serving on my committee, and also thank you very much again for the intriguing questions, and I would like to wish you a nice weekend.
You're welcome. It's a pleasure to serve in this committee. Have a nice weekend.
Thank you.